Okay, so the first problem is, I'm looking at the questions right here, the orbital distance for geostationary satellite. Okay, so I've already started with the picture here. I want to find this distance r. So here is my satellite going around the Earth, and I want this to take 1 day, one sidereal day, not one solar day. Look up the difference. It'd be a good little exercise for you. Okay, so let me just call that time to go around TD for sidereal day, or day, the time. Okay, so I want to know, let's say, the angular velocity. Okay, if I know the time and I know it's 2 pi, then I could say omega for geostationary orbit would have to be 2 pi over TD. Okay, so that's how the angular velocity I want. Okay, now let's draw the forces on this. Here's my satellite, and the only force I have is the gravitational force that way. And that's going to mean that the change momentum is also that way. So if I call that way the x direction, then I have Fg magnitude equals dp dt magnitude. It's moving at a constant speed, so that means that this change in momentum with respect to time will be due to circular motion, so I can write that as P V over R, where R is the radius of the circle, which I'm going to call little r. Okay, so let me put, this is just going to be mass times velocity squared over r, or I could write that as mass, since omega equals v over r. I should probably switch this to little r. Well, you can handle it. So v is omega times r, so this is m omega squared. Okay, I am switching to little r. Little r matches that. So that's the change in momentum. Now I can put in the gravitational force, g, mass of the Earth, mass of the satellite, over r squared. That's the magnitude of the gravitational force, m, satellite, omega squared, r. Now, what did I want to solve for? I want to solve for the radius, the orbital distance. Okay, so let's just algebraically solve this. I get r cubed equals, this mass cancels, equals g mass of the Earth over omega squared. Is that right? Check it. So let's see, r cubed divide, yeah. So r is going to be the cubed root of g mass of the Earth over omega squared to the 1/3. And I can put in omega squared is it's going to be 4 pi squared over t squared. So this is going to be g mass of the Earth td squared over 4 pi squared all to the 1/3. Okay, and you know, me, done. I think that's done. But let's just get a value, because I know you like to put values. So g is 6.67 times 10 to the negative 11. M is 5.97 times 10 to the 24th. And TD is the time for a sidereal day, which is 23.93 hours, but you need that in seconds, because these other g is in terms of seconds. So you can convert that to seconds. I'm going to put the numbers in. I'm going to give you the answer. I'm moving right over here to my calculator. It's on my computer, right here. I'm not going anywhere. Okay, see, I'm still here. Can you hear me? Okay, so I'm typing in g times the mass of the Earth times TD squared divided by 4 times pi squared, all of that to the 1/3 power. And I get, oops, no, I made a mistake. Got to put parentheses around that, because otherwise it will multiply by pi squared, and I get, boom, no, error, pi. I didn't like that. I thought I imported that. Oh, I didn't. let's say pi equals 3.14, and then put that in there again. Okay, so I get 4.2 times 10 to the 4.2 times 10 to the 7th. See, I'm back. 4.2 times 10 to the 7th meters. Now, just compare that to the radius of the Earth, which is 3.6 times 10 to the 6th. Radius of the Earth is, did I say 3? It's 6.37 times 10 to the 6th. So it's way out there. These geostationary orbits are way out there. Okay, now let's do the same thing for the next part. Says, what is the orbital distance for the space station? Okay, I don't have to do anything. I don't have to do anything else because I didn't put in numbers, see? If I want to do the space station with an orbital period of 90 minutes, that just changes this to 90 times 60. That's the only thing I have to change. And I can solve for the new R. So let's do RISS for the International Space Station. That's what that's stands for. So let me just change TD equals 90 times 60. And then I will put the same calculation in there. And I get 6.653 times 10 to the 6th. 6.653 times 10 to the 6th. Not very far compared to a geostationary orbit. It's not that much higher. This is 300 kilometers above the surface of the Earth. Okay, so not very far. Now, the second thing I said was, what's the fraction of gravitational force at this height compared to mg? Okay, the gravitational field. So let's just do this calculation. So let's do Fg over mg, right? Because this is, and the masses cancel. So this is going to be g, mass of the Earth, that's it, over radius, and this is the radius of the space station, radius ISS squared. That's the gravitational field, and then divided by the gravitational field in the Earth, little g. And that will give me the percent of gravity in the space station. Okay, so if I just put in g times mass of the Earth, divided by, then I had, I should put that down, 6.6533 times 10 to the 6th times 9.8. Oh, I gotta square that, I'm sorry. And I get 0.918. So this is the important point. In the space station, the gravitational field's almost the same value as on Earth. It's not that much different. Okay, boom. That's question number 1.